And then the highlight of today is RAIDs, which stands for redundant arrays of inexpensive disk. So since this is inexpensive, we can be redundant, right? If this were expensive, we can't be redundant, obviously, right? That would be too costly. So uses multiple disks to build fatter, bigger, and more reliable. We want all the good stuff. So advantages over a single disk would be, obviously, we have a performance gain because we use multiple disks in parallel. We'll have bigger capacity. And now since we have redundancy, we'll have reliability. Redundancy means, hey, I have copies, right? By the way, just to digress a little bit. So in Korea, if you go to work, your job is secured. Unless you're like a senior management, like a VP. So if you go to Samsung, for instance, if you rise to the VP level, you're on a yearly contract. They review your work every year, right? So the reason the Korean companies, the leaders don't do like forward-looking stuff is that you need performance now. Because you're going to have an interview every year. Oh, you didn't help a product make money, you're fired, right? So 1 year. Now, let's say you go to Samsung as a regular person, you'll never get fired unless you commit crimes, right? You know what I mean? Your job is secure. Anyways, so what I'm getting at, so I just use the word fired, right? So the US, now being fired means you did something horribly wrong, right? Let's say you leaked the data, whatever, intentionally. You get fired without, so there's fire with cause. Now there's something called being laid off, right? Company, the market's not great, we don't have a profit. So 20% layoff means in the workforce, 20% of the workforce will be laid off. And usually they'll give you some severance, like pejigum, right? So those called laid off. And then being fired versus being laid off, very different. Now, the reason I bring this up, if you go to UK, England, British, do you know what they call that? Because you know in English, there's English, American English, very different. Do you know what they call this? Being fired? You're from Europe, right? You know? So they say, I became redundant. Yeah, that's what UK term. So please don't make me redundant. Yeah. Other ones, famous ones are friend, mate, right? British friends will never call you friends. Hey, mate. Okay. Friend, mate. Okay. Apartment. You guys live in an apartment? Which apartment? You want to go back to my apartment? If you go to UK, you want to go back to my flat? With a different accent, obviously. Very different, fascinating, actually. So the English we learn in Korea is actually American English. If you meet somebody from British, very hard to understand, like even the simple words. Yeah. Anyways, I digressed again. Anyways, redundant is RAID, but in a good way. Now, what's fascinating and awesome about RAID is it's transparent to the system that uses them. What this means is that if I want to replace a disk with RAID, just do it. No need to change anything else. You don't have to change your code, nothing. Right? Get the disk out, put the RAID in. So when a file system issues an IO request, and we're going to now separate logical versus physical. So if it issues a logical request, Then RAID will calculate which disk possibly pearls to access to complete the request and issue one or more physical I/O. If it's redundant, then you might have to look at which one, right? And possibly both, depending on you're trying to read or write, which we'll get into a little later. So RAID system is really a separate hardware box, and it has a standard connection like a SCSI or SATA to a host. You just plug it in. Internally, it's sort of like a computer, right? It has a microcontroller that runs the firmware. It has DRAMs, in some cases, non-volatile memory. Now, since we're talking redundancy, resilience to failure and all that, we'll have to touch on a fault model. And what we're going to do is look at the fail stop. So fail stop fault model, disk is either working or failed. There are only two states. Either works or it failed. Working means all blocks operational, can read or write. Failed, nothing, can't do anything. Very simplified, but we're just going to use that. And also we're going to assume when there's a disk failure, we can detect it. Sometimes in reality, not the case, but again, for simplicity, we're going to assume this is detected. So we're not going to consider complex failures such as disk corruption and all that kind of stuff. So we're going to go through different RAID systems, and we're going to try to evaluate each. So we're going to have three different metrics. One is a capacity. So let's say we have a given set of n disks, right? Because we have multiple disks. Each disk with n blocks. Now, with that redundancy, right? Like a single disk, this will be, capacity would be n times b, right? N disk, n blocks. Now, let's say we mirror it, meaning you copy it. Let's say for one, we have 2 copies, right? If you want to have more copies, fine, but let's just say 2 copies. Then the capacity would be n times b divided by 2. Reliability, instead of number, we're just going to think about how many disk faults can the given design tolerate. Performance, as we know, and as we've seen, it depends on the workload. With that, we're going to go through 3 or 4 different designs today. RAID level 0, which is striping. Level 1 is mirroring. Levels 4 or 5 has redundancy, but uses parity. There's also RAID levels 2, 3, and 6. We're not going to go through it. Some of them aren't even used, but these are the key ones. So let's delve into it. First one is striping. So key here, no redundancy. What it does is stripes blocks across the disk. 0, 1, 2, 3, 4, 5, 6, 7, right? In a round robin fashion. Now, the blocks in the same row, this is a stripe, right? So it's just a line, right? So that's level 0. Simple enough. But let's say we could also have some variance here. Could have a bigger chunk size, right? So what we could do here, let's say if a chunk size is small, now then many files will be striped across many disks, and this increases the parallelism of read writes to a single file, and increases the positioning time to access blocks across multiple disks. But now, if you have big chunk size, this would reduce intra-file parallelism, right, within a file. And then you're going to have to rely on multiple concurrent requests to achieve high throughput, right? So let's say here, if the chunk is large, then each would take up 2 blocks, right? So in level 0, you have a bigger chunk size, then you can just use 2 blocks in one. So for performance analysis, capacity, there's no redundancy, right? So it's still n times b, so good capacity. Now, in terms of reliability, if there's any disk failure, you're done, right? No redundancy, right? So bad reliability. In terms of performance, all disks are actually being utilized and often in parallel to serve user I/O requests. So it has excellent performance, unless there's a failure. Now, in terms of performance, we said, okay, depends on the workload, but there are some other metrics we want to use. The first one is called the single request latency. So just one request, how long does it take? So this basically shows you how much parallelism can exist during a single logical I/O operation, right? Because the more parallelism you have, the faster it is. Steady state throughput, this is total bandwidth of many concurrent requests. In terms of workloads, again, we're gonna have two different ones. Sequential means just keep doing it. So you're gonna spend little time seeking and waiting for rotation, right? Because it's one next to another. So transferring data is the time you spend most in this workload. On the other hand, random, you're gonna have to seek and wait for rotation, right? So different workloads. Now, assume that a disk can transfer data at S megabit per second for sequential workload and R for random. Obviously, S is much larger than R. We're going to assume a sequential transfer of size 10 megabytes on average, for random 10K. We're going to use the average seek time of 7 milliseconds, rotation time 3 millisecond, transfer rate of a disk is 50 meg per sec. So for 10 megs for sequential, the amount of data is 10 megs, time to access would be 7 plus 3. 10 meg divided by 50 here is 200, so 100 megs divided by 210 millisecond, resulting in about 47.62 megs per sec. For random, it's a 10K byte, but now you're gonna have a different number here, right? So yeah, the transfer time is different. So now your performance is about 0.98 watt. Now with that, right, and we're going to use this for different RAID designs. Now let's go into RAID 0. Now, for random write and random read, again, no redundancy. So this is just N times R. Sequential, again, this is N times S, right? Simple. Again, horrible resiliency, but that's fine. So now RAID level 1 is, okay, we need to have some redundancy because when the disk fails, it's horrible. So we need to have a mechanism because, again, disks are inexpensive. So let's have redundancy. So make more than one copy of each block. Now, each copy is on a separate disk, right? Because if you put in the same disk, that'll be really stupid, right? Because you want to have a disk failure, but you still want to be able to recover that, right? Be resilient, have redundancy. So obviously, if you, let's say 0 will be on a different disk, 1 will be on a different disk, right? Key here, separate disk. So you can tolerate disk failures. Now, let's assume for each logical block, RAID keeps 2 physical copies. If you want to have more resiliency, redundancy, you can have 3 blocks, for instance, but your performance will be much worse. Now, the example here, we call this RAID 1.0 because this is really RAID 1 plus RAID 0. Because we use mirrored pairs, which is RAID 1. So these are mirrored pairs, but they're also striped on top of them, right? Which is RAID 0. Okay. Now, when I want to read, I can read from any, right? Reading is something you don't change the content, right? So I can read whichever is faster. Write, on the other hand, you need to be consistent, right? So you need to update both. Typically, you do that in parallel because they're in separate disks, right? So let's analyze. In terms of capacity, since it's mirrored in 2, so it's n times b divided by 2. All right, capacity now half. In terms of reliability, you can tolerate failure at any one disk. Let's say if disk 0 failed, you're still fine because I still have 0246. Now, if disk 0 and 1 failed, then you're in trouble. I can still go with disk 0 and 2 failing at the same time, right? Now, in terms of performance, first, latency of a single read request, same thing as RAID 0. I just go read, right? In terms of single write, right? Now, I need to write both. We're going to do this in parallel, but one might take a little bit longer, right? So the worst case of a write is my latency for a single write. Now, for a steady state throughput, sequential read write, you know, n times s just divided by 2, right? In terms of random read, again, this is same as 0, RAID 0, so that's n times r. In terms of write, you need to do this twice, so you divide by 2. So that's RAID 1. Again, maybe in terms of performance, capacity, less, but much, much better in reliability compared to RAID 0. Now, let's go to level 4. So if you mirror, guys notice, my capacity got divided by 2. That's huge, right? I mean, let's say, I don't know, like, you have money X. Let's say, hey, just keep just half. That's too much of a sacrifice. So can we be smarter, right? So that's level 4 using parity. So for each stripe, we're going to use a single parity. And this stores the redundancy information of that stripe of blocks. And we do that using XOR. So you guys are probably familiar with it, but if there are even number of ones, the value is 0. Otherwise 1, right? So example, let's say we have 0011, right? So we have 2 ones, so your XOR is 0. Here just have 1 1, so XOR 1. Now, obviously, if you do a bit, you just do it bitwise, right? So the first bit here in this stripe, 0 1 1 1, 3 ones, so parity 1. Now let's look at in this stripe, the second bit, 0 1 0 1. So we have 2 ones, so this will be 0. Right? So instead of using half for redundancy, we should be able to recover failures without spending half because we use parity. Now, just for optimization, so when we're writing a big chunk of data to disk, RAID can perform an optimization at full stripe write, meaning if there's a write request of blocks 0, 1, 2, and 3, you calculate P0 and you write all blocks. including the parity block to 5 disks in parallel. Okay, because you need to calculate the parity, right? So you just wait until you just can do it in a full stripe. So in terms of analysis, again, we use single parity, right? So we use a single disk for the parity. So we're going to say a log n minus 1 here, right? So the capacity is now n minus 1 times B. Reliability, you can tolerate one disk failure. So if this 0 is failed, you calculate your parity, then you know what this will be. Since we have single parity, if there are multiple disk failures, you're kind of screwed. Right? Obviously, there are different ways to do this, but okay, out of scope. So single disk failure, we can recover. In terms of performance, yeah. So sequential read, write, random read, basically simple stuff. You just have to replace n with n minus 1. Okay. Now the interesting part is random write. Because when you're trying to overwrite a block, that means you might have to also update the parity block, right? So there are different ways to do this. Let's say a block is updated. Additive parity would read all other data blocks in the stripe, also in parallel, do an XOR again, and then write the new data and parity to the respective disk in parallel. Okay, so you read the entire row. Makes sense. However, here the issue is, let's say I just change one block, but I still have to read all in the stripe. Right? So can we actually be more efficient? So the subtractive parity. Let's say we overwrite C2 here with C2 new. Now, if C2 old and new are the same, right, updated but same, then the parity is also the same. However, if the C is different, then you just have to flip the parity. That's it, right? Now, if you try to represent it mathematically, this is it, right? Where this symbol is XOR, right? So if you don't trust me, go do it yourself. This works. So here, right, you don't have to read the entire stripe. So the performance now is R divided by 2. Now, what you might have noticed is that, first of all, for every update, we have to update this disk. Possibly not all, but most of the time. Also, what if this disk 4 fails? Right? So that's actually pretty smart, right? I mean, compared to RAID 1, I think this is excellent. But there's always room for improvement. So we have now random 5, but I kind of jumped the gun here. There's also I/O latency. Sorry. Yeah. Now, single read latency, this is basically same as a single disk request. Now, write, you need 2 reads, right? Because 1 plus parity, and also 2 writes. All right, so this is twice of a single disk. Now, for level 5, which is better than level 4, we have rotating parity. So the parity is spread across different disks. So, yes. So we don't have problem we just talked about for RAID 4. So this is very similar to RAID 4. So we would have the same capacity, same failure tolerance, same sequential read write, and same single request read write. Random read might be a little better. In terms of random write, now we're gonna have NR divided by 4, where 4 is basically because due to each write generating 4 IOs, right? 2 read, 2 writes, 4. But this is still better due to the parallelism. Yes. So the comparison table is for you to enjoy. We won't go through. We went through most of them anyways. So that's that. So other interesting rate issues that we haven't delved into, like I mentioned, there's levels 2 and 3. There's also level 6 that tolerate multiple disk faults. And I'm guessing this would be covered if you take the operating system graduate level course. You could do things like, I can have a spare. This fails, I can just use it. We use a very simplistic fault models, but there could be very different things. Then how do you recover it? So that's also interesting research problem. There's also software rate systems as well, but yeah, these are just for your reference, out of scope of this course. That's it for today. Yes, sir. Okay. What slide number was that? Yeah, actually, yeah. You know what? This one? 30 or 39? Am I in the right slide or where?
I thought the distance between the point and each gets determined by the difference of the number of bytes.
Can you come again? So here, you select the request with a minimum seek time. So it depends on my head location, current location. Right.
If the content is there are 2 regions, 12 and 17.
12 and 17. Where's 12? Here, okay. Yeah.
Then it's like the 17, right?
No, but you're rotating this way. 17 is already passed. So this is not actually a physical distance. This is the actual time. So here, 12 would come in R over 2. 7, because you're rotating this way. Right? Yeah. Yeah. So I mean, I don't know that YouTube video, but depends, right? Now, if we're rotating the other way, then obviously we want to go 17, right? Right, because you know what I mean, right? Because this would have to go all the way back here. Versus this one, you just wait half, then you'll come. So you just have to move here, wait for 12 to come, versus 17, you have to circle around the entire circle, right? Because it's a seek time, not the position of your current physical distance of the current head, right? Because it's all about the direction. Right. That's why it has to, that's why it's a scheduling, it needs some computation, right? It needs to look into seek time, rotation delay, and so forth. Yeah. Yeah, go ahead. 49. Small chunk size increases what? Which one? Increase the positioning time to access blocks across multiple disks. So across multiple disks. I think what this means is, so if you have blocks, so here, because now if you have larger chunk size, right? So these could be different blocks in the same disk. So you don't have to do positioning, right? That, I think this just means that because you're not gonna have these two chunks on the same disk, right? Because all chunks are small. So when you have to go to a different chunk, sometimes you might have to, it takes time to go into look for a different disk. No, you're trying to read something, so you still have to do, so even if this is not an issue of parallel, when you have to read something, right? If I have to go to a different disk, unless you're actually reading both of the same. If it's in parallel, yes, but there was a question on this side. Yeah. Can you, okay, RAID 4. Analysis, okay. Do we need to use? Can you repeat? I'm sorry. Am I in the right slide?
Yes.
This one? Okay. So yeah, so for our analysis, we use subtractive because it's faster. Yeah, yeah. Maybe I missed it. So we don't have, so we don't want to be reading, we don't want to waste a reading operation for something that hasn't changed. So because that was what additive parity did. Very simple, intuitive, but I need to read the entire stripe, right? Because I changed a block. And then what it does here is it read in all other data blocks in the stripe. Although in parallel, it's still an operation, right? Yeah. So this is for random write. So reading is still the same. So for random write, in order for us to do the write, here we divide by 2 because we only have to write the block that's changed and the parity. Yeah. But you're saying, I get your point. So here what you're saying is, even if we do additive parity, I do more reading, but in terms of writing, you're saying I only need to write these 2, right? Yeah, I guess that makes sense. So this could still apply no matter which writing methodology you use. Mm-hmm. So this is, okay, so why there's no term n? So you're just doing a write. It's just a random write, right? Because in this case, we're just, so random write means in a random workload, I have a write operation, right? So it doesn't really matter how many desks you might have, right? Because if you're doing, yeah. Sorry, is it really? Yeah. Yeah.
Why?
Yeah. Okay, so here. Right, so you're saying, why do we have 4 here, but not in rate 4? Is that the question?
Why is the world is
Oh, here. I see. Versus, what was the other one? Yeah, I actually can use here. So in random, right, why do we have n?
I think it's because for rate level 4, because the participants are all in the same distance.
Right,
Can't really take advantage of the number of disks, because if, for example, we're writing on disk 1, number 1, and disk 2, number 7, and there's on rate level.
rate 4. This one, Yeah.
So we're writing on number 1,
right,
and we'll both have to write on 0 and 1.
right,
Comparing it,
right,
and do that.
right, 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 right. Yeah, good point. Thank you. All right. Used up almost all the time. So yes, thank you for the questions and answers. See you next Monday.